Well, actually, you were supposed to say that.
Sorry, that's okay. All right. So, first of all, questions thus far. Projects are ostensibly due tonight at 11:59. If they're coming late, I don't care. Just generally speaking, because in all likelihood I will not get to them, seeing as somebody who spends time at various other places. All right. So, questions thus far. I know you've got a question which I've got queued up. Any others? All right. Let me address a little bit of Matplotlib plot before we get into some math. All right. So first of all, you need to do at the top of your file and usually we import this thing as PLT. Oops, go here it is. All right. So this gets you started. And there's a bunch of concepts that you want to keep track of. There's the notion of the figure window. The figure window is a finite state machine. It holds information about what you have thus far plotted. Figure windows have under them axes. And under the axes, there are plot objects. And specifically, the typical kind of plot objects that you want to talk about are things like lines, or patches, or fills, or text. Many other such things are plot objects. You can dig into the documentation and take a look at the gallery. There is, associated to the Matplotlib webpage, there is a gallery of examples that go from the very basic to the insanely complicated. And furthermore, they'll have working code that you can just download, try out, or take a look at on the webpage. So you see lots of these sorts of examples. But let me
say patches?
Patches.
It's a patch.
What is a patch? Okay, so if I have a little line segment, a bunch of line segments, something like this, a bunch of line segments, a patch is what happens when you take this thing and you fill it in.
It's not a fill?
Depending on how you access it, there's slight technical differences between patches and fills. And you access them in slightly different ways. Okay. So associated to an axis are axis limits, like something that would say, roughly speaking, -10 less than or equal to x, less than or equal to 12, and 5 less than or equal to y, less than or equal to 15. Things about whether or not this is linear or a log scale. Things like titles. Axis labels. All of these things here are axis properties. And so, yeah?
What's the relationship between the plot object and the axes?
So plot objects have to be on an axis. They are drawn with respect to the coordinates given by an axis.
Okay.
So what you'll generally see when you're drawing stuff on a window is you'll pull up the figure window. Here's your figure window. There'll be the official window title. Maybe a close button here or something like that. So you'll have that up there. That's the figure is the actual operating system's window that you're drawing into. And then you have a bunch of axes. So for instance, you might have an axis here and another axis here. And associated to this axis, there's some coordinates, 0 to 10, 0 to 5, and then this one, maybe this is here, so you have something like -10 to 10, 0 to 8, something like that. So you have two axes. You can label the axis. Or not. You can only label one of the axes if you want. And then you can put some plot objects into this thing. And the plot objects can have color, maybe you have something that amounts to a regression. Or maybe you've got something that is, what you're plotting over here is an actual, I don't know, abstract simplicial complex. So the theory of operation is you build them kind of in this order. You build the figure window, build the axes, fill them with plot objects. Now, the axis step is sometimes not needed. See, here I've drawn the two axes. If you just do one axis, then the state machine that drives this plotting really just assumes that, that if you just start feeding it plot objects, it will say, okay, I'm going to make you an axis because obviously you want one. And there's really only one that you need to refer to. And so often when you're dealing with those kind of examples where you have just one axis that you're plotting, then you'll never see the axis generated. It'll sort of be implicitly there. When you look at the code, you'll see it just refer to PLT. Okay, so now let me dig this apart a bit and show you how this machine works. Or rather, give you some examples of commands that are useful to talk to these various features. And actually, worth noting, the theory of operation is almost exactly the same as what goes on inside Matlab. So if you happen to use Matlab, this is the same plotting language. And it's actually kind of roughly based off what goes on in OpenGL, which is another language, or another state machine. It's not really a language, it's more of a, it's an API for describing 3D graphics. Okay, so the way you usually start your plotting is you pull up a figure. So if you do plt.figure, it will pull up a figure for you. If you want, optionally, you can store that figure and talk to it directly. Say figure 1 is plt.figure. That's optional. You can also refer in here to a figure number. I want to talk specifically to figure number 1. But that's optional. You don't have to. Now once you've got your figure up there, then you can start feeding it things to plot. For instance, you might have something like this. You might want to plot something. If you want to plot that thing, and you have a vector of x's, this is a numpy array, another numpy array of y's, then this will plot them. And this plots them with lines. Little line segments between the points. So this is parametric plot with line segments. If you want to plot discrete points, they don't have anything related to one another, you can start adding additional styles. So for instance, if you want to plot them with little plus signs, you do like this. So this is individual points marked with plus signs.
So each point is a plus sign.
Yep. Now there are various other plot styles you could give there as well. If you want to mark them with dots, you put a period. You want dotted lines, you put a colon, and there's a whole host of other ones. You can look at the documentation and find out. You can change the color. If you put an R in front of that plus sign, you'll get red. A red plus sign. So
Quote R plus.
quote R plus, give you red plus signs. Quote G plus will give you green. And then there's a whole bunch of others, like K for black, B for blue.
How would you change colors of the line segments?
Same way. Okay, so in fact, if you don't list the plus sign,
You just do comma R.
just comma R in quotes, and it'll do it red.
Okay.
Very simple.
So to find out about this, we do help and then parentheses plt.plot.
Yeah, depending on exactly the Python interpreter you're using, there are various ways to access this. Got it?
If you were to only pass in a list with, say, 1x and 1y value, would that just plot point?
That would plot a single point.
Cool.
Yep. So if you just want 1 point, that's one way to do it. Now, the hazard here is, if you're plotting a line segment with 1 point, it might not show up.
Yeah.
Because it might be just one teeny little pixel worth. So it's useful to use the markers,
Okay.
so that they've got some size to them. because otherwise you might not see it. Okay, now, for instance, say in this example here, I've got a whole bunch of things. I've got a bunch of lines and, a regression line, and a bunch of points. I want to have them all up at the same time. This figure window is a finite state machine. It holds some state, has some memory. So what you can do is you can ask, I want to plot something, and then I want to plot on top of that, keeping the old thing. This says retain whatever you've got in the current figure window and just add to it. So this is plot cumulative. If you decide you don't want that anymore, of course you can pass plt.hold false. These guys can be tagged off instead of PLT, they can be tagged to figures, so if you want multiple figures up there at any given time, you can. You can also explicitly ask for an axis. So inside your figure, you can ask for an axis and build into that, but we don't need that for this particular project. Okay, so you can turn things on and off. You can label things. plt.title does what you think it does. Put some text in here. plt.x or y label does what you think it does. And there are two more that I tend to use frequently, and that's plt.xlim and plt.ylim. What they do is they set the axis limits. They each want to accept a tuple where the first entry of the tuple is your lower bound and the second entry is your upper bound. So in this particular plot here, that's what they want. But actually any sequence type will work too. So you can certainly pass a list or even a generator function if you so care. That would kind of be overkill, but anyway.
If you don't give it a limit, does it just snap to your data?
Good question. If you don't ever call these, yes, it will snap to your data. This can have kind of weird effects when you're doing hold. So usually when I've got the hold on, I explicitly choose the limits. Because what will often happen is that, for instance, say I'm drawing this line, this regression line, I've got a bunch of points. I don't necessarily know where the data lie exactly. I want to have the regression line kind of extend outside. I don't want to snap to the size of that particular line then. And so then I explicitly set where I'm viewing just on the points, so the regression line kind of goes off the screen.
Could you explain plot hold again?
Okay, so what plot hold says is it says, think of it this way. In MATLAB it's hold on, as in I'm not done, hold on.
Okay.
Let me keep adding to this plot. In this case, hold true says set the hold state. Hang on to whatever I've got and allow me to accumulate.
Okay. So if I wanted to plot like a bunch of points.
Bunch of
and then
points.
more points on top
And
of
then
those
more points on top, say with a different color or whatever.
Okay.
Absolutely. Or in the case of simplicial complex, maybe you want to plot a bunch of fills in one color and then a bunch of other fills in another color, and then on top of that a bunch of points.
So it allows layering.
It allows layering, yes. This allows layering. And it plots from back to front. So the deepest layer is drawn first, the top layer is drawn last. So for instance, if you want to make a nice looking simplicial complex, start with the fills to draw all of the two simplices, then draw the lines, and then finally draw the points. So that it looks kind of nice that way.
If you don't tell it to hold, where does it get rid of it?
You just see the most recent. Other questions? Yeah.
So if you say patch and you give it 4 arguments instead of 3, like four different coordinates, so 4 different points.
Yeah.
What it's going to do is it's actually going to
Trace out that
draw
line.
like a quadrilateral and fill that in. It's not going to
Yes.
get like a tetrahedron or
No.
something. Okay.
So yeah, so these are meant to be either lists or NumPy arrays. They're iterable again. And so if you're asking for a patch, it will just fill in that region as best it can. I mean, essentially what it tries to do is it tries to fill out, it's not quite a convex hull, it's kind of like that region. So it tries to come up with a bounding region, closes off that loop, and fills everything on the inside. Now, if you give it something stupid, and like your points are in this order, you will not get a rectangle. You'll get a bow tie. Yeah.
So do all of these things return some kind of plot object?
Yeah.
Okay.
Yeah.
So, once we've created the plot object, so we name it object,
Yep.
can we then call
Okay.
methods on the object?
Absolutely.
Right, so could we call, say, object.plot this if I wanted to do more things to it?
Yeah, you can. This syntax is meant to mimic Matlab
Right,
and Matplotlib.
yeah, it's meant to be functional.
Well, it's meant to be finite state machine
Mm,
rather than object oriented.
Okay.
Now, under the hood, Matplotlib is object oriented. So yes, there's a list of methods that are like this. The names are slightly different to avoid name collision.
Okay.
Yeah.
So how do you actually name one of these up? So you could be working with multiple graphs at
You
once.
can. So usually the way I do this is I do it like I'm programming in MATLAB. I make a figure, I plot a whole bunch of stuff in it, and then I make another figure. Plot a whole bunch of stuff, make another figure, plot a whole bunch of stuff in order. Because then the finite state machine knows which one I'm working on the most recent figure. Now, one final point. If you run all of this thus far, nothing will show up on screen.
You have to do a plot.show.
You have to do a plt.show before anything will show up. Do not forget this, or you will be very sorely disappointed.
I mean, it's doing it.
Yeah, in fact, what it's done is it's built it in memory and it's waiting. The reason for this is you can do crazy things like double buffering, etc., to get better animations. So you can build a whole bunch of these things. Maybe it takes a long time to draw a bunch of these plots. So you pre-build everything, and then if you want an animation, then you successively bring them up very quickly once they've been pre-computed.
Is there a plot.clear?
There is.
Okay.
I don't know if it's clear exactly, but there's something of the sort. I think it might be CLC. Again, based on that. One final bit is if you want to save these things, you can do a plt.savefig and give it a file name.
So that's going to save, so when you start up Python, you're starting it up wherever.
Wherever.
So start up in directory X. So that's going to save it as x/stuff.
Yeah, whatever's in, it saves it in your local working directory. Yep, so, and incidentally, you do not need to do a show in order to do a save fig. Benefit of this, when you do show, it stops execution and waits for you to close all the figures. If you want to do a big long batch process where there's lots of things happening, not on this project, but just generally speaking, this doesn't stop execution.
So the current working directory of Python though is where you started up.
Unless you've changed it, yes. Yes, there's a sys module that allows you to manipulate that. Yeah.
So the argument of that figure function is just a 1?
Well, it's an optional argument.
Oh,
It's
okay.
blue, and it is the plot. If you wish to have several different figures in play, and you want to go back to one, you can go back to it by figure number, or I think you can even pass the thing with figure object as well, to set that as the current state.
Oh, okay. So if I were calling an old
Figure that's already up there, you want to add to it.
Okay.
Yep. It's a little bit more complicated dance, which actually I don't remember exactly offhand. It allows you to manipulate these things in a non-blocking way, as in put up a figure and allow the execution to continue. It's a little more complicated than just PLT shell.
You can spawn a new,
You can certainly spawn another thread and keep that live, and that's essentially what happens under the hood.
can't do that, you have to spawn a new process because Python is global interpreter lock.
Sure.
Yeah.
Yes. That's part of the reason why there's a little bit of complexity.
It's the multi-processing module won't you do that.
Yep. Okay. Other questions? This make sense? All right. Okay. So now switching gears away from programming towards some math, and specifically towards, we've thus far talked about persistent homology. I've kind of intuited why persistent homology is a good thing to do and better than just pure homology if you're starting from data. But I haven't exactly really shown you what that means. And so today I want to tell you what that means. This is, in some sense, some of the practical aspects of doing persistent homology. And say robustness. This basically comes back to two papers. One by Brunner and Harrer, and the other by Steiner. Roughly speaking, early 2000s. Harrer, H-E-R-E-R. John Harrer, yep. And the other by Steiner and a whole bunch of others.
H-E-R or H-A-R?
H-A-R-E-R. Still very much alive and kicking. All of these people here are active researchers now still, doing interesting things, many of them still in this space. So this isn't it. Math courses very rarely get up to the current time. We're basically talking about stuff that's just back from the cutting edge. This is very recent as far as mathematics goes. And the idea is, if I modify my data a little bit, does it change my persistent homology? How does it change my persistent homology? The question is, how do small perturbations of input data change persistent? We already know that if I got rid of the word persistent, small perturbations in my input data can cause pretty large perturbations in the homology.
Does that mean homology is chaotic?
It's not chaotic, it's just very sensitive to noise. It's not very robust. Even though it's robust to continuous deformations, but it's not robust to statistical variation. Persistent homology is it is not a topological invariant anymore, but it is statistically a lot more solid. So the point is that homology is topologically but statistically brittle. It's easy to break plain old homology. Persistent homology fixes the latter, but gives up on the former a bit. It's approximately but statistically robust. So what do I mean by approximate topological invariant? Well, that's what I got to show for you. Is in particular, if I make a small change in my space, some small noise-like change to my space, I expect to get basically the same homology out. Because I haven't changed the topology. But of course, if I change the topology, all bets are off. It would be quite different. Okay. So now what I want to do is I want to walk through the statement and a little bit of the argument in these papers. These papers get a little bit technical at points, so I want to sort of convey the main ideas that I think are worth keeping in mind when using these tools. It is worth noting, remember, that persistent homology in degree 0 is just a form of clustering. And clustering is known to be something that is reasonably robust. So when people do data mining, you've probably heard of machine learning or big data processing, that sort of thing. Well, essentially what people are typically doing there is they're trying to do something that's a little more souped up of a regression in some fashion. The most basic regression in the world is, well, this point is A or it's not A. It's class A or it's not class A. Sort of a hypothesis test in that regard. My data lying in one area or not. You can think of it as a regression in some fashion. I mean, not like linear regression by any means. It's more of a set valued regression. And persistent homology is doing that in degree 0, but it does more. Okay, so what do I mean? Well, first of all, I need to tell you, if it's approximately topologically invariant, I need to give you a way to measure the difference between different computations of persistent homology. I need to give you a metric on barcodes. Okay, so let's do that. That's the crucial technical tool that starts off these papers, is writing down the idea that I have a metric on the space of barcodes. At that point, then I can talk about continuity. And I can talk about what happens to small perturbations. Okay, so let me do that. And let me sort of give you broad brush what's happening first, and we'll delve into the details. Okay, so the idea, the main tactic, is a metric on the space of barcodes.
Can we think of barcodes like vectors?
Kind of. They're not quite vectors, but they're more like computer science vectors, as in lists of numbers. They're more like that kind of vector than they are like Rn kind of vectors. But there's kind of a nasty little problem that barcodes are not themselves that robust either. You need to visualize them in the right way. And need an encoding of barcodes in a way that exposes the difference between small and large perturbations. Put another way, the difference between very similar and very different barcodes. And this is an encoding called persistence diagrams. They're exactly the same information that is otherwise written in a barcode. They're just written in a way that's a little more amenable to making the metric on them. And so what I want to do is I want to give you by picture, because the picture is very explanatory, how to turn barcode into a persistence diagram. Okay, and what is a persistence diagram? Well, it looks like it's a two-dimensional plot. It's a bunch of points in that two-dimensional plot, although they're points that could be counted with multiplicity. I'm allowed to duplicate the points, and maybe two of them in exactly the same spot. That's what I mean by a sort of computer science list, like duplication's allowed. On the other hand, order doesn't matter. Technical terms, it's a multi-set. A set in which duplication is allowed, but order doesn't matter. Okay, so persistence diagrams are going to look a bit like that sort of two-dimensional plot in the first quadrant.
So keep hanging on to that again. So, for instance, 3, 3, 4, and 3, 4 as sets would be different sets.
They're different multi-sets.
Multi-sets.
They're different multi-sets, but they're the same set.
Yes.
That's right.
And this is the persistence diagram as an object,
Yes.
as a multi-set?
That's right. So,
Okay.
We'll get there in a moment, we'll see why that is. Okay, so let me draw a barcode diagram. Remember, under the hood, a barcode is something that, let's add this one right here. Barcode is something that really is descriptive of what? Descriptive of a sequence of vector spaces. Got under here, these are describing the different kinds of bases. These are describing the basis elements of a sequence of vector spaces, one getting mapped into the next. So keep in the back of your mind that that's what's going on, although they don't actually play a role quite yet. They play a role in the theorem we'll write, but remember, it's something like this. But there's a sequence of vector spaces and linear maps between them going on that's given rise to this. This is describing the bases of each of these vector spaces and how they've intertwined. Okay, so now what I'm going to do is I'm going to take this same information and I'm going to encapsulate it in a diagram. And the way that diagram is going to work is, well, each of these bars are characterized by two numbers, when it starts and when it ends. As in, which vector space index it starts at and which vector space index it ends at. Now, just to keep things entirely concrete, let me label these bars. So I've labeled the bars. Remember, they're telling me something about my vector spaces. So what I'm going to come over here is I'm going to tell you when the bars start and where they end. That information is going to be a bunch of points over here. See, this one started at index 0 and say ended at index 1. As did this one. This one started at index 0, ended at index, say, 2. This one here started, I don't know, 5 or 6 and ended at sometime later. So really you need to label these then with the start and end. Usually in the persistence literature they call this axis the birth axis. When did this particular basis element, when was it born? And then naturally this is the death axis. When did it die?
So is the birth the same birth we were talking about in terms of when the simplex shows up?
Exactly the same.
How does a simplex die?
Simplex doesn't die, but that homology generator can if I have, say for instance, a loop that fills in. That loop will have died at that stage once it's filled in. Or I may have two connected components that are separate. When an edge comes between them and joins them up, one of those connected components dies. Of course, up to basis change, it could be one or the other, it doesn't really matter. Okay. So, of course, you're not allowed in here. You can't die before you're born. Because that would be, this barcode is sort of read the other way, that doesn't happen. So each one of these particular barcodes then ends up as a point in the first quadrant above the line y equals x. Okay. So then, for instance, this A and B, they're born at time 0, they die sometime later. A is here, as is B. C is born at time 0, dies sometime later. Here's C, and here's D. Now what about E? Well, E is not born at time 0, it's born at time 1, and dies after D. So born at time 1 dies after D. Now F is born a little bit after C, and then dies shortly thereafter. So born a little bit after C, this is when C is born, and dies a little bit later. So there's F. And G is born after E has died, and is really only around for a little bit. So there's E, so there's G. So first of all, right from this simple example, there is the multi-set nature of this exposed because I have an overlapping point and I keep track of both of them. A and B are both represented by the same point there, so I remember the fact that I've got two of them there.
A comma B is a multi-set?
Well, A comma B is there, and so this whole structure has to be a multi-set.
Oh, so the multi-set is referring to
The
the whole.
multi-set is referring to the whole diagram. So a persistence diagram is a multi-set of ordered pairs. I'm going to give you now the formal definition. Definition, a persistence diagram is a multi-set D in which all of the points are of the form x comma 1, where x, the birth, is less than or equal to the death. Not quite a set, but a multi-set. So that's a persistence diagram. Now, I do include the equal sign. The reason why I include the equal sign, which means I include all of these points on the diagonal, the reason why I include that is because there's something kind of funny about that. See, I could well have, if I imagine, rather than being discretely sampled, imagine taking the limit in which I have many vector spaces. And I have a bar that exists just for that one moment, and then immediately dies. That allows me to capture that. And what's interesting, now let's look over there, those short bars are awfully close to this diagonal. Turns out, interestingly enough, if you play around with barcodes and play around with persistent homology, you will realize that those points kind of near the boundary, or kind of near the boundary of this region, so the line y equals x, tend to come and go rather frequently. While these guys tend to hang around, these ones tend to persist a bit more. Yeah.
That's right. No.
Okay. So the important observation actually can be crystallized into a theorem that says there is a notion of distance on the set of persistence diagrams. And that notion of distance is one that fits very well with some kind of notion of distance that gave rise to the points that were compared to persistent homology up. Now, in order to do that, I need to be a little bit more concrete about how I came up with the persistence diagrams in the first place, and which spaces I am building my filtration out of. Because thus far I haven't really mentioned spaces at all. I've just mentioned these kind of diagrams. And the choice of spaces could matter, and in fact, in general, it does. So I need to constrain that. But before I do, let me actually give you the distance metric here that you can use. There are several different ones out there. The original one mentioned by the papers that I referenced make use of something called bottleneck distance. Is a metric on the set of persistent diagrams. Like so, persistence diagrams like that, these multi-sets, such that, or rather given by a formula, actually, it's given by an explicit formula. The bottleneck distance between diagram number 1 and diagram number 2 has a very particular form. That very particular form, make sure I get the form written down correctly, is you do a 2-stage optimization. Okay, there's a bunch of notation here, and I'll make this clear in a moment. And gamma, from D1 to D2, A by injection.
You feel them over the path and
Gamma is a bijection. Not necessarily a path, no continuity constraints. No continuity constraints, it's just a bijection.
I think it's
What's that?
I think it's, I haven't said infimums of effectively, infimums over functions.
Well, basically, okay, so think about it this way. I've got a bunch of points.
Yeah.
I've got another set of points. If they're the same cardinality, there exists a bijection. List all such bijections, maybe an awful lot of them, but list them all.
Okay. And then just take the small.
And just take the smallest, or the greatest lower bound over all such.
Okay.
It's kind of an awful thing.
Yeah.
From a computational standpoint, this is bad news,
Yeah.
like in the extreme.
Which is probably why other people have to find different distances, right? To try to get rid of that, or no?
No,
Okay.
no, actually. The different distances primarily are in playing with this norm here.
Okay.
So this norm is the infinity norm, which what it does is it picks the maximum of either the difference in the x-coordinate or the difference in the y-coordinate. Pick the larger of the difference in birth times or death times. Now, as I just alluded to Janelle, people have messed around with this and selected other norms here. There's a whole family of norms that play better. So this works well enough as far as establishing robustness. But if you want to talk about something like an average persistence diagram, you need some kind of structure in D, or in my space of diagrams, so that I can actually write down what an average is going to be, and I need to be able to do some kind of like convex operations. This doesn't play very well with that, kind of. So you need a slightly different one. Anyway, nevertheless, the proof is easier in here. Yeah?
Question for you. Is it, because when I see the
Yep.
infimum, the kind of thing that I'm thinking about is like least squares regression. Is
Yeah.
that sort of correct or no?
Kind of.
Okay.
It's kind of like that, but it's like totally, completely nuts.
Okay.
Because I'm optimizing now over a very likely, infinite collection of functions.
Mhm.
Very likely, uncountably infinite collection of functions. Now, the other thing too is this definition here doesn't quite well work with the bottleneck distance. There's a reason. What can go wrong with this definition? How could this fail to be well defined? I mean, intuitively, this is the right thing. And intuitively, what I've written down is right. Well, how could this fail to be well defined? Yeah.
The infimum might fail to exist.
Yeah, the infimum might fail to exist. Why? Infimums usually exist.
There'll be multiple things that satisfy the infimum?
Yeah, that's fine. It's just going to be a number then, nevertheless. I mean, an infimum, I'll let it be negative infinity if it's empty. That's fine.
Oh, okay, so if we allow it to be negative infinity, then it can't not exist.
It can't not exist, but negative infinity is kind of bad for distance.
Sure.
Isn't the infimum of the null set infinity?
Yeah, I guess you're right. Fine. But
D1 and D2 are different sizes?
yeah, if D1 and D2 are different sizes, then we're going to run into this problem you guys are bringing up. Because then there's no bijection.
Oh.
So then, in that case, then I'd be forced to pick infinity. And that's kind of no good. So the way we fix that is we force a bijection to exist by fiat. How do we force bijection to exist? I'll modify my definition a little bit here. I force this to contain at least all the points of the form x, x. Include the entire diagonal. So my persistence diagram is not only a multi-set of the points in red that I've marked here, these are the points in red, but it now also includes the diagonal. Once you've now included that diagonal, that fixes this problem here. Now a bijection certainly exists. Why? What's the cardinality of D? Yeah, uncountably bad, uncountably big. It's the same as the unit interval.
And as long as you've got two things in L of one, you can.
Yes.
Election. One.
Yes,
Yeah.
that's right. So this is now big, so now I get lots of bijections. And now it's game on. Well, I mean, provided you want to deal with like an uncountable number of bijections. And iterating over that space, like looping over them.
But in theory,
In theory, it's fine. In practice, it's kind of pain in the
But
neck.
how is something of cardinality ALF1 iterable?
It's not.
It's like you start at 0, and what's
That would
next?
not be countable.
it's not an iterable thing. That's
It's
what
not
you can't do
iterable,
it by a
that's-
computer.
You can't do it by computer.
It's for theory purposes.
It's for theory purposes. So this particular theorem that was written in these papers is at this level of theory. Now, when it comes down to practice, what you do is you do iterate in some fashion. The way you do it is you say, well, how do I deal with the fact that I can have lots of real numbers? Like in the real world, by which I mean like statistically, what do?
You sort of approximate.
Random samples. You take a distribution on this space of bijections and you pull them out randomly. Now you end up with, eventually in the limit, you end up with the right thing, provided nearly everything is nice. That's kind of a difficult theorem to prove, as you might imagine. Kind of a scary theorem, but okay. And actually, one that came much later, now of course, in the span, we're talking 10 years or so ago, that came about 5 years ago.
How would that guarantee that you get?
It's very, very subtle, very delicately depending on this is purely on diagrams. It doesn't work on the level of diagrams. It works on the level of diagrams coming from very definite spaces.
Okay.
It requires some regularity condition to be imposed on the spaces that give rise to the diagrams. Okay, now, all right. So I'm purporting this is the right metric in which we're going to talk about robustness. Now I need to now come up with those spaces. And I'm going to take the approach given by these two authors. And the approach to that is to use a lot of regularity. Now, they leave the comfortable, discrete realm, and they go into a little bit more of the smooth domain. So we have derivatives and such, but that's okay. And the way they do this is they work with something called a Morse function. Is a Morse function. F is smooth, which means any derivative of f, including all the partials, exists and is continuous. So take any derivatives you like, put it there, they're continuous, all is well there. And, parenthesis, now defining smooth for you, any derivative exists and is continuous. Huh?
F is D1. Or C2.
Yes.
F is at least C2, it's probably quite a bit more.
Right.
Yes, F is C infinity. Take any derivative you like, any one at all.
Okay, you're right.
We're good. Okay, and other feature of this is that at a critical point, matrix of second partials is a full rank.
Is that the Jacobian?
That's the Hessian.
Hash?
That's the Hessian matrix.
I haven't heard of that name since I was in mathematical econ. I took mathematical econ as a sophomore.
What does this mean? This means that if you're at a critical point, it's definitely a maximum, a minimum, or one of those various kinds of samples. So in particular, you can take that Hessian, that matrix of second partials is automatically symmetric by the smoothness. And because it's a full rank, it doesn't have any zero rows or columns or whatnot in it. And you can diagonalize this thing symmetric matrix, you can diagonalize it. And this is the key point. You can diagonalize it so that there's a bunch of minus and then a bunch of pluses. So, and the rest, everything else is 0. So you can diagonalize the Hessian so it looks like this. And if you take the number of negative eigenvalues, that's called the Morse index. So this now, a lot of technical machinery there. We've really souped up the level of calculus machinery that we're using.
Is this the second order condition for maximization?
You will get maximization when you're at a top Morse index.
Right.
That is a maximum. You get minimization when your Morse index is 0, and everywhere in between you have various saddles that are unstable.
Right. So I think that's what we use the Hessian for.
Of course, that's what you use that Hessian for. Now, important observation here is actually the reason why topologists like Morse functions, and they certainly do. In fact, there is a famous paper, Morse Theory Indomitable. It is a wonderful, well-loved paper, in which they do all sorts of cool things with Morse theory, as you might suspect. The great thing about Morse functions is that topological changes on the level sets only happen at critical points. So if you take the level sets of this function, topological changes in those level sets only happen at critical points.
So you have level set instead of level curves here?
Yes. And in fact, those level sets are topological spaces.
So that's where like the connected components of, and you could also do this with
Morse, all right, look. So Morse theory is like an entire course all on its own, and I can get seriously distracted because it's one of my favorite things in the world.
Okay.
Uh,
Got it. Can you leave that formula on the bottom, just for?
I got it if you want.
Oh, yeah, that's fine. Yeah.
all right. Okay.
It's probably a little hard to write that in Notepad.
Oh gosh, unless you're doing LaTeX.
Yeah, that's pretty good.
Okay.
I'll lay
Anyway.
it later.
Anyway, all right. So key point here is that, and this is called I don't know what I want to call this thing, but it's basically one of the various Morse lemmas. So I'll put it as a proposition. Topological changes of f inverse of minus infinity comma a only occur
Yeah. You want to get through the pointer.
at
And that's what the if is over.
critical values. And a critical value is a critical value well, when is a good critical value? It's when the derivative at the point, take a look at the pre-image, is if f x equals a and x is a critical point, i.e. where the derivative of f is not a full rank. Critical point, fill that up in here. And as I said, this can get very sophisticated very quickly. Morse theory is a very powerful way to analyze the topological structure of a space. Surprisingly, there are lots of Morse functions. In fact, they're generic, which means if you've got, actually means several things, but first of all, if you write down any function at all, there's a Morse function arbitrarily close to it. That's kind of handy, so Morse functions are quite common. And the other thing that you can do is you can generalize up from Rn to any kind of thing that kind of looks like Rn up to manifolds and do Morse theory on them. And then these critical topological changes allow you to actually decompose that space in a nice fashion. Yes?
Here, the derivative of f at x.
Yep.
The total derivative, and is thus the
Yep.
Jacobian matrix?
Yep.
Yay.
Yes, indeed. Total derivative. Yeah, I could write that. Total derivative is full rank. That's right. Now, in this case here, the Jacobian matrix is a what shape array? What shape is it for this particular guy? It is
N by N.
n by 1. N by 1. Jacobian matrix is parameterized by the range and the domain and the codomain. So this total derivative is not a full rank. It's basically saying that I don't have a zero vector. Okay. All right. So lots of setup. Now the key theorem that comes back to persistent homology. And as you might suspect, now this is the key thing. These objects here, these pre-images of these particular sets, pre-images of these particular sets, topological changes happen at very specific points. And so I'm going to make use of that. And here's the theorem. And this is the one that is due to error. Is that if f and g are Morse functions, then the bottleneck distance associated to the homology of, oops, minus infinity to a, so the diagram associated to this homology and the diagram associated to this homology. So I have two spaces. I want to know their homology. Yeah, I think I got enough for one. There we go. All right. So associated to these two spaces, I form persistence diagrams by varying the A. That is bounded above by the difference in functions, measured in the appropriate fashion.
I would love to see Professor Casey have written that expression. When I would think him missing brackets and me catching them, he makes fun of me for it.
Well, you know, actually in former life I programmed a lot of Lisp, so I'm kind of used to parentheses.
Exactly.
As the name of the language, LISP, means Lisp processing. Yeah, sure. Lots of irritating, spurious parentheses. Is what happens when you're programming. Okay.
You pick up an eye for detail very fast.
Yes, you do. All right. Anyway, so now my notation is a little bit weird. I mean the persistence diagram. Due to the filtration, the homology of the filtration, like so. So the obvious thing that's happening here is as I slide A from minus infinity on up, as I slide from minus infinity on up, varying my A, I'm going to hit a bunch of these critical values, and each time the topology of that pre-image changes. But at every time, if A is less than B, then I will get this kind of inclusion. So as I slide from minus infinity up to plus infinity, my space gets strictly bigger. So I get an actual filtration. That actual filtration is then something I can write down the persistent homology of. In principle, if there's a finite number of critical points. So that's the final statement. And And in particular, what you need to have is you need to have distinct critical points and distinct critical values. They're separated in some fashion so that the topological changes happen at very distant, very specific times. Yeah?
They also be finite number.
They do not actually have to be finite. They do not have to be finite, but they need to be far enough apart that you can draw a line in the sand between them. To say that what's happened on this side versus that side.
Okay.
So you can't have one of these kind of parabolas stretched out where the maximum of, the global maximum is actually just a line.
Yeah, that's not going to be a Morse function.
Yeah.
Why? Because the Hessian, that second derivative is going to, that matrix of second derivative is going to be 0, not a full rank.
Gotcha. Okay.
Yeah, that is not a Morse function. So, let's get some pictures here, because this formula is kind of heinous, as stated. Let's get some pictures about what they mean. Here's X. So here's F. Let's take a look at what some of these level sets look like. Well, when A is kind of small, let me draw a bunch of A's here. This is one of the critical points. This is another one of the critical points. So this function has 2 critical values. Before this critical value, or less than this one, I'll call this one, let's say this is 1 and this is 2. So the preimage of F.
Aren't the inflection points also? No.
Nope. Up to, say, 1/2. What does that look like? Well, that looks something like this close set. The next set I'll draw is after this particular critical point has been gone through. What does that look like? Well, I've gone up a little bit, but now I've picked up something in here. So the topological change that's gone from the green set to the blue set is this guy showed up. I've started filling in this little basin here as I've raised the water level. Actually, what? Let me move these guys up there a little bit. This one's fine. Move them up a little bit. So you can see where they are in relation to everything else. That's this one. The blue one is at 3/2. So what's happened is as I've slid this line up, I touch right here at 1, the critical point. Start filling up this basin as well. So that's been a topological change going from here to here. This had 1 connected component, this has got 2. Now if I continue on my way, say to 5/2. Now I'm up here. I've included all of these points now. So this one is here, and this one is here. So what's happened is as I've filled up 1 connected component, 2 now, and then back to 1. So these are the topological changes that a Morse function will give you. Now, you get lots of other ones too. Now, that's F. We've got G. Let me draw a G. Make it dotted. Let me make it just a little bit different. So that's G. Bunch more critical points. Bunch more critical points. I've now added 1, 2, 3, 4 critical points rather than 2. What ends up happening? Well, for a little bit of time in here, I get an extra connected component that isn't present in It isn't present in F, but it's present in G. So in particular, if I now sort of green dotted, I'll put them next to each other, what is this particular level set? The G inverse, this set look like? Well, it look almost exactly like. Almost exactly like the F level set. Now what about the blue one? The blue one looks almost exactly like it. Also, it showed up a little earlier. It was born a little earlier. It was born a little bit earlier. But basically, from a topological standpoint, they look pretty close to being identical. So that's the G inverse 3D halves. And certainly, when we get big enough, there's nothing further to say up here. But the only time that there's anything really different, and I got black here, the only time that I've got anything different is right in here, where I have three connected components. Now what I want to do is I want to transfer this diagram of the actual level sets themselves into a persistence diagram. Okay. So for F, what happened to F? There was one particular connected component that was born, well, whenever, right? It was born a long, long time ago.
The galaxy.
And a galaxy part, yes, of course. Of course it had to. Way down there somewhere. It was born way off the page there. And that connected component's been around for a long time. And it's going to continue to be around for a while. Let's make a definite point. Let's just consider everything above 0, just to keep it simple. So it's born at time 0. And when does this green connected component die? This very first one here, well, it sort of merges and then it peels off a piece, and then later it remerges. Maybe it never dies. So let me just mark this kind of by saying blue green arrow, saying that this component is born at 0, never dies. All right, let's not consider that for the moment. Now the other thing that happens with the F's is I get this filled in spot here, the blue one. The blue one is born at time 1 and dies at time 2. Born at time 1, dies at time 2. There's time 1, my scale diagram that would be 2. So this is for F. For G, that same point just happens a little earlier. It's born a little earlier, and it dies a little later. Born a little earlier, dies a little later. That's the same one for G. That's this dotted component. This black one, though, this guy here shows up at some point, and dies not very much later. So it's born sometime between 1 and 2, so in here, and it dies a little bit later. That's also true. So here now is why the bottleneck distance matters. The bottleneck distance, remember I include all these points on the diagonal. So the bottleneck distance looks at a bijection between them. Well, I could have a bijection that matches this point to this point, or any point on the diagonal. Well, of course, that's going to give me a fairly large distance, because I'm going to have to match this point also to the diagonal. I get a much smaller distance if I match this point and this point together, and match this point to the diagonal. And that is, in fact, then what one does to get the minimum. In this case, it's very easy to walk over all of those infinite bijections, and just to match up this point with that one, and this point directly to the diagonal. And all the other points in the diagonal just there too. Yeah.
Why is it at G has two different locations?
Because it has something that was born here. This particular filled in basin as we were sliding up, that one showed up, and I got an extra teeny little component here that showed up and then went away a little later.
Oh, okay.
And that little one that showed up and then went away very quickly, that was G. And since it got matched to the boundary, it's kind of noise-like. Something that's not very robust. But this one here, these guys are much more robust to perturbation. Because there's sort of this large-scale dip. So that's sort of the idea of why this particular metric is the right thing to use. Yeah,
Aren't you already mapping that line to itself?
I am. But it is uncountably infinite, and I can certainly pick any other projection I like that makes a little room and stuffs that point.
It's we can freely add or remove things that measure zero.
Oh, God. Uncountableness gets us out of a jam in this particular case. That's all I had. So we'll see you guys on Wednesday. Thank you. All right. The silver button. Yeah.